Okay, chemistry time. We have here on the board, I'm going to keep this up for just a second. We have here on the board some examples of how to calculate the energy of a quantum and the energy or the energy of a photon using Planck's constant. And so I'm just going to keep this up here for a second so that if you need to refer back to that, you can. And the second is up. You can pause the video, obviously. Let me get my fat head out of the way. There we go. You can pause if you need to. Okay. Now, we're going to move on to something called electron configuration. This goes along with quantum mechanics. In my mind, we kind of did the concepts, the conceptual, intellectual framework of the lesson yesterday. And today we're going to do the, we're going to really plow this field by doing the actual work. We're going to do electron configuration, which I will show you the worksheet. Let me just do that right now. You can pause this too. There, worksheet.
Make sure you flex your wrist and it's going to say, my name is Hund.
I don't know.
Yes, you do.
Okay, so today we're doing electron configuration, so let's write that down, please. This is something that we do.
Wait, are we doing the worksheet or are we doing another page?
We are doing this. I would put this in my notes. This is a discussion. You're free to formulate some useful, please, input, but it does need to be. I would put it in my notes. I don't think that would be a discussion. That would be more like doing the worksheet on the video.
I know, then the kids next year who do this,
it's going to be really easy.
You can watch my video, and if they do, they get rewarded.
We will do examples. We will do examples. We will do examples, and those may end up being on the worksheet. Now, you need to know 3 conceptual things. Now, I just said this is something we do and not really something we think about, but you do need to know 3 things about this, and they are the Aufbau. This is in German. Aufbau principle. The Aufbau principle. I believe that the word Aufbau is German for least or undermost. The Pauli exclusion principle. Pauli exclusion principle. And Hund's rule is the last one. Hund's rule. Hund's rule. Let me write these down for you first. The Aufbau principle is that at their ground state, which is the lowest amount of energy they can have, electrons fill the lowest energy level they can. Let me write these in a different color. I think you can see that pretty well. Oh, no, you can't see the word Aufbau. I did it too wrong. Boop. I'm going to Cupid shuffle on up here. There we go. Aufbau.
You didn't even move it.
Yeah, I moved it by degrees. Hepatitis. Okay. Hund's rule, I'm going to have to be careful of how much I write in there. Aufbau principle. So the Aufbau principle is that electrons fill the lowest available energy level. The Pauli exclusion principle is that only one electron of each spin up or down can, don't switch to cursive, the kids don't like that, can occupy each suborbital. What?
What does that say? Is it say only
Fill, that obviously is not what it says. It fills the even lowest available energy level. I did my best. I did my best. Only one electron, this is the Pauli exclusion principle, only one electron of each spin. Electrons can have 2 spins, up and down. What are the 2 spins of an electron?
Up and down.
Up and down. Only one electron of each spin can occupy each suborbital, and we'll talk about what that means in a second. And then Hund's rule, which is that, I'm trying to think of a nice, simple way to phrase this. Each suborbital in an orbital, oops, spell it right though, you moron. Watch your mouth, you moron. No, watch it. In an orbital. Who said that? Who's talking? It's still me. Each suborbital in an orbital contains 1 electron before any contain 2. Basically, they each get 1 before any of them get 2. Kind of like, let me give you a little example of this one. This one's like, if you fill up one of your cups with tea, the tea goes into the lowest part of the cup first until that part's full, and then it fills up the rest of the cup. That's pretty basic. This one, I think this one's kind of self-explanatory, but you can, other than the fact that there's a suborbital, which we'll talk about, but every suborbital, which can contain 2 electrons. How many electrons can a suborbital contain? 2. Every suborbital can contain 1 up and 1 down electron, and no more and no less. That's not true. They can contain less. They can contain 1 or 2 or 0, but it cannot contain more than 2.
You know how that makes me think of that? Okay.
Suborbital.
Suborbital. You can have 1 or you can have 2. You can have a 6-inch subway or a 12-inch.
There you go. Yeah, suborbital, sub-sandwich, 6-inch or 12-inch. Yeah. And like this, you can have a left 6-inch sub and a right 6-inch sub, but you can't have 2 lefts. That doesn't make any sense. Sub, or I like that analogy. I'm going to use that every year from now on, Taylor. Great. And then Hund's rule is that basically everyone going through the lunch line has to get firsts before anyone can get seconds. All of the suborbitals, for an orbital, all the suborbitals have to have 1 electron before any of them can have 2. Now we talked about orbital shapes. We talked about orbital shapes yesterday. The orbitals come in, we show them in this way. 1s2. This is how we show electron configuration. I'm going to show you what these things mean. 1, then the lowercase s, and we do not, here this is the mark of someone who doesn't know what they're doing. If they say this as squared or raised to the 2nd power, you know they don't know what they're talking about. Because we pronounce this 1s2. We pronounce this 1s2 is how we say this. In this case, obviously in math, we would say that is squared, so don't be throwing shade on the math homies, but 1s2 is how we would pronounce this for electron configuration, where the 1 is the principal energy level. What we would call like an energy level 1 electron or an energy level 3 electron is its principal energy level. The S is its shape. You should have in your notes from yesterday, and if you didn't watch that video, it's still available, but you should have in your notes from yesterday the different shapes of the suborbitals. Shape of orbital. Sorry, just the orbital, not suborbital. And then 2 is the number of electrons in the orbital. Shape of orbital. So this is the principal energy level. Is here are the 1. S tells you the shape of the orbital, and the 2 says the number of electrons in the orbital. So the electrons, we're talking about this. This is an atom. This is its nucleus. These are, when we draw it like this, remember, atoms don't really look like this in real life as much as they look like anything. They don't really look like this. But we would call these the energy levels, principal energy levels. And in reality, each of those principal energy levels is made up of different or one or more shapes of orbitals. So that one, the first energy level is a sphere. The second energy level is 6 lobes of a 4-leaf clover and a sphere. And that's called the principal energy level, but the shape are these shapes here. And then the suborbital would be like this one dumbbell shape is one suborbital. So a suborbital can contain how many electrons, remind me? How many electrons can be in a suborbital?
1.
No, 1 or 2 to be in a suborbital. And this one, if this one is up, the other one has to be down. It has to be. Subway. Eat fresh. Subway does not sponsor this video. Other brands are available. So what we do is for any given element on the periodic table, see these? For any periodic table element, we can tell its electron configuration. Here's how it goes. Look at the there's a picture of what we call the aufbau diagram, which you can pause on the video or you can look on your book on page 156, but this is called the aufbau diagram. Starts with, everyone has to have this open. You won't be able to do this without this. We start where on this aufbau diagram?
156.
It's on page 156. But according to the aufbau principle, we start where on the aufbau diagram? Let's say whatever atom we're talking about only has 1 electron. Where do we put that 1 electron? Out of all these, On the very bottom. You girls need to pay attention. You're going to have a very hard time with this. Do you have your book open to page 156? No. Okay. So if we have one electron and only one electron, we put it in that bottom box. What's the bottom box's name? 1s.
Since this is in my book.
I'm not gonna draw all of them. Shh, please be quiet. 1s, 2s, 2p, 3s, 3p. Let's draw that much of it. So let's say it has one electron. Where do we put that one electron on the aufbau diagram? On the very bottom. It doesn't matter if you pick up or down, but you can only pick up or down. Okay, now look. What do we call that? Well, it has one electron, and that electron, if we were writing its electron configuration, we would say it's 1s1. Has one electron, the shape of the orbital is s, and it's in principal energy level 1. What element is that? What element has one electron? Hydrogen. So hydrogen is and always will be 1s1. Now, let's move on a little bit further. Let's do beryllium. Look at beryllium on the periodic table. I'm going to erase our diagram for hydrogen. Let's look at it's number 4. So how many electrons would beryllium have? 4. How many electrons does beryllium have? 4! Thank you. So we have 4. Beryllium right here has 4. So let's put them in. Where do we put the first electron?
1.
Yeah, according to this aufbau principle, we put it in the bottom. Where do we put the electron number 2?
At 2.
No.
At 1.
Yep, still 1. Now it's a down 1 though. Where do we put electron number 3?
At 2.
Yeah, we go right up, and then the fourth one?
Right down.
So we call beryllium 1s. How many are in 1s? 2. And then 2s2. That's beryllium, and that's done. How many total electrons does this have? We count up the baby numbers. 2 plus 2 is 4. How many does this one have? 1. Let's do another example. Let's now do silicon. Let's make it a little bit harder. Look at silicon on your periodic table.
14.
Has 14. So we're going to put in 14 arrows. Where's the first one go?
1.
1s. So, okay, second one?
2.
1s2, 2s1, 2s2, 2p1, 2p3, 2p2, 2p3. Now listen, this is, excuse me, this is Hund's rule. That everyone gets firsts before anyone gets seconds, okay? So then, 2p4, 2p5, 2p6. How many do we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3s1, 3s2, we're at 12. 3p1, 3p2. So we write all that out. Silicon is 1s2, 2s2, 2p6, 3s2. I hope in yours you put it 3p2. I hope.
3p3 is
Nope.
lower.
No, and then, yeah, that's right. In this case, what we would call, so this is x, y, and z. The 3pz is empty. You don't necessarily need to know that, but that's just a matter of interest.
It's record.
So if silicon is 1s2, 2s2, 2p6, 3s2, 3p2, what would phosphorus be? All of that but 3p3. Sulfur would be 3p4. Chlorine, 3p5. Argon, check it out. Argon, now you can see, fills the 3p. So argon is all of that, 1s2, 2s2, 2p6, 3s2, 3p,
3d.
no, 3p6. Good.
What about something that would be greater?
Then you go to 4s.
What's right up from 3p? Then would be 4s. So then after argon goes to 4s. If you had to guess, we did hydrogen, we did beryllium, we just said that potassium would be 4s1. If you had to guess, this little box here, which one are these all going to, which letter are these going to have in them? No. S. In fact, I almost every year when I do this, I show you on the periodic table with sticky notes that these ones should all end, when you write out their electron configuration, these ones should all end in S. What do you think these ones over here should end in? P. We call that the P block. what do you, if you had to guess, what would you guess about these ones?
D.
D. Good job, Gabe. And these ones down here,
It would be
no, this one's D.
F?
F. So when you're, as you're doing them, if you end in a number that isn't, or a letter that isn't these, then you've probably done it wrong. Now, someone noted that this is kind of gets pretty lengthy. There's one other trick that we have, which is called, so this is called the aufbau diagram. This is a way that people use when they're learning this. They fill up the aufbau diagram. This is a way that when you get good at it, you can just kind of do on your own, like I just did. This is called electron configuration notation. But then there's an even briefer way called noble gas notation, where you go from the configuration of the last noble gas, and then you start where it is. So, for instance, if we were doing potassium, the one we just said, that ends in 4s1, we would put in brackets argon, meaning the entire configuration of argon, and then 4s1. So that's potassium. Could you do potassium like this? Yeah, but it would take up a lot of space, which is okay. But it's easier to write like this. Potassium is argon, 4s1. Now, sometimes you'll have to be able to do this because you can't always do this. Sometimes the instructions will say, use electron configuration notation. Other times it'll say, use noble gas notation. And, just so you know, when you do krypton, the noble gas notation, you can't just put krypton in brackets. That's not its noble gas notation. Its noble gas notation is argon, 4s1, 3d10, 4p6. You'll also notice, as we look at this chart, this will be the last thing before I set you free, and you'll need more work, obviously, and we will do more examples, but for the video, you'll also notice that if you go up from 4s, what's the next one? No?
If we go from 4, you did 3D?
Yeah, it's 3D. 3D has a lower energy than 4p, but it has a higher energy than 4s. So what we do is it actually goes 4s2, 3d1, 3d2, 3d3. So it goes back down in energy level. What that tells us is that these transition metals are actually filling up a lower energy level than their highest one. Meaning they don't really gain more. What do we call the outermost electrons, by the way? This is one of your vocab words. Valence electrons. And that should be everything you need to complete this worksheet. So we did actually none of them that are on here. But that's okay. You should be fine. Bye. It never works the first time. Bye.